So now we're going to listen to the last speaker of ECCV 18. Is Yuchen Yuan, who's going to speak about multi-attention, multi-class constraint for fine-grained image recognition. Please.
Okay. So glad to be the last one. You guys must be tired. Maybe get a break soon. So good afternoon, everyone. My name is Yuchen Yuan, coming from the Department of Computer Vision Technology of Baidu. Today, I'm going to introduce our new method in fine-grained image classification, named multi-attention, multi-class constraint for fine-grained image classification. And here comes today's contents. I will first present the problem formulation and existing challenges, followed by our methodology, as well as the introduction of our new dataset, Dogs-in-the-Wild, and finally, our experimental results. So classification is a fundamental problem in deep learning. Fine-grained image classification, on the other hand, is a more challenging branch because we need to deal with images with very little differences. For example, just look at these examples. How to differentiate two vehicles like a Volkswagen Sagittar and Volkswagen Passat with extremely similar color and appearance. And look at these birds, how to differentiate them. They're extremely similar in color and appearance too. So fine-grained image classification is designed to address these challenges, which aims to identify the subtle differences between extremely similar classes. Okay, so how does fine-grained image classification work? A typical idea is by the attention mechanism. What does that mean? The idea is quite straightforward. So we first focus on the discriminative regions. For example, these two kinds of dogs. A fine-grained image classification method should be able to locate their most discriminative regions. In this case, their heads and tails. And then, after we acquire these discriminative regions, we extract their features and use the features to do the classification. And now our work is done. And our proposed method is just based on this attention mechanism. So let's see our proposed method. We design our method, which has the following contributions. Number one, we propose the one-squeeze multi-excitation, or OSME module, which aims to locate multiple discriminative paths inspired by the latest ImageNet winner SENet. We also propose the multi-attention, multi-class constraint, which is the MAMC constraint, which works to coherently enforce the correlations among different paths in training. Last, we also propose a new dog species dataset, which is large scale and have high category coverage, data volume, and annotation quality. Okay. So here comes the whole framework of our method. In training, it works like an unparametric learning way. We take image part as the mini-batch, where each pair contains at least two images from the same class, with one as the anchor. And a mini-batch should include at least two classes. So these images first go through the backbone network to extract their CNN feature U, followed by the OSME module. It works like this. So suppose we define two potential object paths or attention regions that we want to learn. For example, in the case of birds, they may be their head and wings. And then the previous feature U goes into two separate squeeze and excitation, or SE blocks. And then we got two channel-wise attention weights, followed by the dot-wise, channel-wise production to the feature itself. And then we got the corresponding attention maps. In our case, there are two attention maps of two classes, so we're supposed to get 4 corresponding attention maps. So these attention maps are then fed into 2 separate FC layers for each attention region to get a final feature vector, and the OSME step is done. So since the same feature U is shared for each attention branch, but their corresponding channel-wise weight is different, and that is why we call it one squeeze and multi excitation block. And finally, these feature vectors of the attention maps are treated by the MAMC loss. I will talk about it later. You can just think it as a new ranking loss here. So the MAMC loss gets with the softmax loss combined as the final training loss. In testing, we input only one image, of course, instead of the n-pair. And the MAMC loss is removed, and the softmax loss is replaced by a softmax layer for deployment. So in short, our method extracts rich correlation features among different attention regions, can be trained end-to-end in one stage, and exhibits good performances. So let's talk about the MAMC constraint in detail here. MAMC functions as a key part in the training of our network. The input is n-pair style, which means that there are 2 images of each class. Let's take a look at these birth images here. If we take this one, the left one, as the anchor, so think about a triplet, then the upper right one should be the one with the same class to the anchor, and the lower right one should of the different class to the anchor. If we take the head as the anchor, then in the upper right one, the head is of the same attention, same class, or SAIC, then that one should be the closest to the anchor than all the other 3 parts. In another case, if we take the different attention, same class, or DSC, or SADC as the positive, then these 2 should be closer to the anchor than the DADC, which are different on both paths. And that's the core idea of the designment of our MAMC loss. And maybe that is still a little bit hard to understand, and let me introduce it in another way. And this page brings another illustration. Let's take a look at the bottom part, which these features, these symbols, are just the different features I just mentioned, marked by different colors. So let's first look at the diagram in the left. All the other features are distributed randomly around the anchor, which is the red in the center. And our mission is to drag the positive ones closer to the anchor, while push the negative ones far away. The SASC is first treated as the positive, while all the other 3 as negatives. So let's take a look at the middle. After one round of processing, the green one, which is the positive one, gets closer, while all the other 4 get pushed away. You may think that is a little bit similar to the conventional triplet loss, but MAMC can do more, which is hierarchical correlations. So after the first round of processing, we fix the green one and treat the 2 light blue ones as the positive, while still the deep blue ones are the negative, and still we drag the positive one closer, well, push the deep blue ones, which are the negative ones, far away. And that's how MAMC works. After the explanation of our method, we'd like to give a brief introduction of our new dataset. We proposed the Dogs-in-the-Wild Dataset. It is a large-scale dataset of dog species with 362 classes and 300,000 images in total. We collect all the images by online crawling. This table shows statistics with some existing fine-grained datasets. It is easy to see that our dataset has the largest category coverage, data volume, and images per class than the existing datasets. And we also show that compared with existing dog species dataset like Stanford dogs, our dataset involves larger intra-class variance and also more surrounding environment types. We conduct the annotation manually by cross-sourcing for 3 times to ensure the quality. The figure in the bottom, by the way, it is also worth noting that the figure in the bottom shows some common bad cases that are completely non-dog from another dataset, but they are hard to find in our dataset. And also, our dataset is publicly released in our website. Okay, so finally comes to our experimental results. We first show that the ablation results on the COB dataset. It is seen that the OSME module alone contributes 3.2% improvement than the baseline, which comes from 81.7 to 84.9. And also the MAMC provides another 1.3, which means from 84.9 to 86.2. With comparable performance level, our method is also more than 3 times faster than one of the state-of-the-art method. So we also notice that a stronger baseline, such as the ResNet 101, of course, provides even better results, although at the cost of efficiency. And then the experimental results, again, the state-of-the-art, we see that our method, we only show the best 2 methods for each data set. We see that our method achieves the best result among all the comparing data sets. And besides that, we also provide some visualization examples, which are done simply by channel-wise averaging of the attention maps. We see that no matter it is on the dataset of birds, cars, or dogs, the OSME module is able to automatically learn the most discriminative and meaningful paths. For example, for birds, it's their head and wings. For cars, maybe their head frames and their headlights. And for dogs, it's their head and their tails. Okay, so in brief, our method acquires attention-aware features by the OSME module. It's supervised by the MAMC constraint. It can be trained end-to-end in one stage. It has good performances. And also, we also released a new dataset of dog species. Okay, so that concludes my talk. Thank you very much. Any questions?
So this is your last chance to ask a question in this conference, so please approach the microphones. Okay, I don't see anyone running. Let me ask you a question in the meantime. So when you compare your method to previous ones, have you noticed that maybe you succeed in different images than others and fail on others, or is it the same statistics?
Sorry?
The mistakes or successes that your method makes, are they similar to the previous method, or can you identify where did you make the gain in performance, in what type of images?
I think the gain, the improvement of performance mainly come 2 aspects. One is from the OSME, which means we acquire the channel-wise weight to the features so that we can learn some attention, which means we find the discriminative regions of the images. And then I think that alone is not enough. We also need to some correlation, some constraints. So that is why we developed the MAMC laws to use these features we acquired and try to drag the positive ones closer while push the negative ones far away. And I think that's why we got the improvement, the gain.
And do you see actually in your results? You can then look at the images and say, I know why this image is correct with my method and wrong with the previous method.
I mean for the data set or for the visualization? Sorry? For the visualization or feed data?
Okay.
Yeah, for the heat map, you mean?
Okay, maybe we'll take that offline. Because I see people want to go to the posters. So thank you, everybody. Okay. I hope we enjoyed ACCV. Should we? I see. So let's thank the organizers of this conference. It was a great conference. I hope you enjoyed it.